The overall goal of this procedure is to store and delay information encoded in optical data packets by exploiting time-frequency coherence. This is accomplished by first injecting an optical data packet into the quantum light storage (QLS) system. For a single packet, the spectral representation is continuous, which means that the difference between two adjacent frequencies of the spectrum is zero. The second step is to multiply the spectrum with a frequency comb inside the QLS system by stimulated Brillouin scattering. This multiplication in the frequency domain corresponds to an extraction of single equidistant frequencies out of the packet spectrum. The multiplication in the frequency domain equals a convolution with the pulse in the time domain. This results in a train of copies of the original signal. The final step is to extract one of these copies by a rectangular read signal. The delayed data signal appears at the output of the QLS system. Ultimately, an oscilloscope is used to show and measure the delay of the optical data signals.
The main advantage of this method compared to other techniques like slow light, where just one bit can be stored, is that with quasi-light storage, several thousand bits can be delayed and stored. Generally, individuals which are new to this method will struggle because time-frequency coherence is used, which is not common knowledge to everyone.
Though this method can provide an insight into the storage of amplitude-modulated signals, it can also be applied to the storage of higher-order modulation formats which use a combination of phase and amplitude modulation.
The experiment takes place on an optical